Hello, everyone, and welcome to the RADNEXT webinar series. And thank you all for joining us today, whether you're attending live or watching this section later on YouTube. My name is Igor Aguiar, and I'm very pleased to introduce today's webinar as part of RADNEXT Initiative, a European project focused on radiation effects testing, irradiation facilities, and radiation hardening assurance for electronics and systems. So before we begin today's technical presentation, I will share a few updates and highlights from the project and the continuation of this community through RADNEXT 2030. So as many of you know, RADNEXT has provided European-funded access to radiation facilities for researchers, engineers, and industry and academia across Europe and beyond. And although the official RADNEXT project is reaching its conclusion by this week, the story does not end here because we are very excited to announce that the RADNEXT legacy will continue through RADNEXT 2030, which will expand even further the ecosystems and availability of facilities. So the first beam time access call will be available around in September, and as I mentioned, an even larger selection of irradiation facility will become available compared to the current project. So if you're interested in future access opportunities, I strongly recommend to keep an eye on the RADNEXT website in the coming months, and also, as I will mention later, on the LinkedIn page for more updates. Over the course of the project, we are very happy that the community has achieved something very truly remarkable. Actually, more than 5,400 hours of beam time have been delivered to users. So we have been able to enable over 200 experiments across multiple facilities and radiation environments. And this number reflects not only scientific productivity, but also an enormous collaborative effort involving facilities, users, engineers, technicians, and of course, project management and support teams for these experiments. So we would like to sincerely thank everyone involved for contributing to this success, and we are looking forward for the continuity of this project. One of the key goals of RADNEXT has always been openness and sharing, knowledge sharing and community building. And for this reason, test reports and scientific publications are openly accessible through the RADNEXT Zenodo repository. So far, we have nearly 180 radiation test reports from user experiments, and we have more than 80 scientific publications resulted from both RADNEXT research activities and transnational access experiments. This is a very important achievement for the field because it helps democratize access to radiation effects knowledge, also improves reproducibility, and supports newcomers entering the community. So I really encourage you to explore the publication list available on the website or on the Zenodo repository. And as mentioned, if you'd like to stay connected with the RADNEXT community, please follow us on LinkedIn page. We post regularly about beam time calls, facilities, scientific publications, webinars, and many other different opportunities related to radiation effects and irradiation testing. And this is another announcement. We have developed in the past few years MOOC, so a massive open online course that is hosted on EDX. And the course is on radiation effects on electronics. And here we have designed a course for 6 weeks, going through from radiation environments and powder-metal interactions to the actual effects in electronics and how to test them. So the course is already available for registration on EDX, and the launch date is 15th of June. And here we have the RADNEXT webinar series that was created to provide visibility to radiation facilities and emerging methodologies and broader radiation effects community outside RADNEXT. And you can find all the previous webinars available on YouTube as RADNEXT channel. And we encourage you to subscribe so you don't miss any of other webinars that will be available. And now moving to today's section, it's my pleasure to introduce today's webinar, continued development of SE test facilities and programs at MSU, presented by Dr. Steve Lidia from Michigan State University, where he will provide insights into the development of single event effects, testing capabilities, and ongoing advancements in the MSU facilities. This is a highly relevant topic for radiation effects community, especially as demand continues to grow for advanced and accessible testing infrastructure worldwide, and that's why we're happy to have Dr. Dave presenting these developments. So thank you again for joining us today, and then I hope you enjoyed this webinar. And with that, I give the floor to Dr. Steve Lidia. Thank you very much.
Okay, I think you need to oh, here we go. Enabling me to share my screen. So let's start. All right. Get rid of that. All right. All right. Can everyone see the screen?
Yes, no, maybe not in the presentation mode now. It's just maybe.
Well, it's just it's an Adobe. It's a
Okay.
PDF. So I think that's probably what we need to do. It should be large enough though, right?
Okay. Yeah, I think should be fine.
Okay. All right. Thank you very much. And thank you for the introduction. And thank you for having me back. It's been about 1 year since we presented, kind of where we were with developing facilities and into, kind of initial ongoing operations for heavy ion SEE test facilities here at Michigan State University as part of the facility for rare isotope beams. So today I want to talk about recent developments and continued developments, where we see ourselves in the next year, the next, kind of 5 to 10 years with the additional facilities we're going to be bringing online. So the abstract is there. I'm going to be talking about a number of developments. First is our basically our recommissioning of our K500 cyclotron and developing that into a dedicated SEE test stand. And some developments, kind of improvements on our infrastructure for handling samples and our dosimetry and the kind of controls and the user interfaces that we've been developing to help users be more efficient with their testing. And then we also have some new developments. Kind of a recent development in this is kind of advancement to a funding position. So we're expecting to see some funding for a second beamline on our linear accelerator. And this will be for the high energy beamline. So we'll have high energy heavy ions available for SEE testing. And then some additional work we're doing with our colleagues in academia and industry on developing the Space Electronics Initiative here at Michigan State University. So let me just dive into all of this. And I'll start off with just kind of an overview. So currently we operate two separate facilities. There is what we call FC, or the FRIB Single Event Effects beamline. This is attached to our first of three linac segments. So this is our lower energy linac that is used to drive beams into a test stand and a user area. The beams there are up to about 40 MeV per nucleon, typically somewhere in the neighborhood of about 25 MeV per nucleon, and they runs the gamut of heavy ions. And it's based on our existing superconducting linear accelerator structure, which was initially designed and is operated as a nuclear physics platform and is capable of generating beams currently up to, I guess we hold a world record in uranium right now at 30 kilowatts CW, and on our way up to several hundred kilowatts CW. So that's the linac portion. The cyclotron portion is over here, and this is using our pre-existing K500 cyclotron, which had been one of the drivers for our nuclear physics program for a few decades. When the linac came online, this one now no longer had a role to play. And so we repurposed it. And so we've developed now a standalone and dedicated facility based on this K500 cyclotron. And we call that KC for the K500. So there's two facilities. Um, Historically, I'm going to run through a little bit of history now with that, with the cyclotron-based facility. It had begun as a standalone nuclear physics driver in the 1980s. There was a second, maybe a third or a fourth, but anyways, there was a second accelerator, or sorry, cyclotron, the K1200, which was also being used around the year 2000 or so. Those were coupled, so the K500 became an injector to the K1200. And then that drove our nuclear physics program from basically 2001 until 2021, when we cut the umbilical to the experimental beamline. A beamline's kind of shown here on the lower right, and connected it to the linear accelerator. But that saw beam powers up to about 10 kilowatts, and it also gave us some initial work on single event effects testing with heavy ions. We had in one of these experimental vaults, we had basically a cart that we could use with instrumentation that we could put in place to allow us to run some experiments. And NASA worked with us early on, and we conducted just a handful of sessions with them. But it wasn't the most convenient facility to use, and it wasn't the most cost effective either. So we saw limited use using these platforms. But with the advent of the linear accelerator, and now with the dedicated K500 facility, we can basically kind of optimize towards running with single event effects experimenters. Um, so in terms of that transition, we had to do a few things. So we had to recommission the cyclotron. It involved moving from a second harmonic operation back to a first harmonic operation. We had a legacy control system we had that we've kept and started to modernize and incorporate into our more modern EPIC-based system. We had to create a new personal protection system. We had to create all new an extraction beam lines and delivery beam lines and user vaults. Um, and so that continued through early 2025, just a little bit more than a year ago. And then integrated system testing was going on last year at this time, where we brought the cyclotron and extraction systems up, and then into user operations as a platform in October of this last year. Um, we've completed, I think, much more than 40 user runs at this point, and our availability is fairly high. So just some pictures, kind of showing the area kind of as it existed. You can kind of see the pre-existing racks, and this is the RF controls up here for the cyclotron itself. We're essentially at this point we're removing all the roof shielding blocks and reconfiguring the vault areas. The old K12, so the K500 is, if you look on the left side picture, the K500 is over on the right, and the K1200 is in this block, kind of shown here, and it's essentially still entombed, and coming out in parts and pieces. But this is showing, 2 years ago, beginning our site preparation. Underneath the mezzanine, you kind of see here. By December of 2024, we had the beam lines basically installed. So here on the top right picture, you kind of see this white object is the cyclotron, with the extraction beam lines moving around this area with these quadrupoles, and then into the dipoles to move it into the user vault. We have a straight ahead beamline and Faraday cup that we can use for diagnostics and tuning operations. A new wall plug and beam stop was installed, so now this produces or allows us to stop the beam in the cyclotron vault while access in basically the user testing vault is enabled. And then we're seeing the beamline established into the downstream section. In August of last year, now we were starting the commissioning, and so now this is showing the downstream beamline section. The octopole and quadrupole transformer is here at the farthest upstream area, and then we get into the dosimetry section, and then the user test section. And that user platform has, is kind of shown over here on the right, showing the 2-inch window, so we can produce beam spot sizes up to about 40 by 40 square millimeters, a mounting plate, rotational platter, etc., to allow for target mounting and targetry. So we've now been operating since September. Our first users appeared in October, and the new facility is now up and running. I'll talk a little bit about the capabilities now. So our initial um, beam list is shown here, and it's composed of basically one large cocktail. So this is a load in the ECR ion source, the plasma-based ion source, so that allows us to produce and to change between any of these beams in essentially the 19.5 MeV per U cocktail relatively quickly. We also maintain a higher energy, at this point, 35 MeV per U, 16 oxygen tune as well, which requires a retuning of the cyclotron and beamline, of course. And this gets us down to low LETs, a little bit less than 1 MeV per milligram per centimeter squared. It's a little bit less popular, but it allows us to get up to relatively low LETs. I'll talk a little bit about the source coming up. So one of the improvements that we needed to do to facilitate fast tuning of the ion species for test purposes was making some updates onto the ECR ion source. So this is an existing source. It's a room temperature source. We actually operate two of these, Artemis A and Artemis B. So Artemis stands for Advanced Room Temperature ECR. The M is ECR ion source. But it's a 14.5 gigahertz source, compared to our high performance source, which is at 28 gigahertz, and that's a superconducting source. And it's based on a very similar source at LBL. In fact, most of our ion sources are developed in close collaboration with Berkeley Lab. This one has been in operation since 2001 as an injector into the K500. We have a second one, Artemis B, which is our room temperature source, and it's another source which we use to feed the linac, the superconducting linac. So we have some experience now and two of these sources in constant operation. Um, the nice thing about this room temperature source and this relatively low frequency now, 14 gigahertz versus 28 or 30 or whatever the high performance sources are getting to these days, is the volume, and the access to the external part of the ECR ion plasma chamber. There is a slotted design in the chamber which allows us to have additional probes and additional penetrations into the chamber that we use now as access for sputtering sources, which we can directly control with power supplies. We also have at the back end um, um, two leak valves to allow us to put in different gas mixtures, and so we typically operate with a gas mixture of xenon and krypton and argon, basically the noble gases as well as oxygen. We can do that from one of two separate lines. And we also maintain a sputtering source. So that's a small oven, which is current driven to heat up, that we can use for other metallic elements, or other elements which we need to bring up to high temperature. Currently, we use that sputtering source for our thulium ions. Kind of a picture here, kind of showing the vacuum chamber and the penetrations. And so in the top right is showing basically a feed through with these three fingers. And so these are our sputtering sources, and they enter into the high radial part of the ion chamber of the plasma chamber, kind of shown here schematically. And we can load them with basically samples, these little coupons of here's silver, there's gold, we have copper and as well as cobalt. I think we had a copper in this for this photo, but we've changed it to cobalt. And we operate them by essentially putting a bias voltage onto those. So we can bias these independently. And when we bias it, we subtly change the plasma surface and we allow plasma electrons to impact on those foils or on those coupons. And that acts as a sputtering source, and then introduces those elements into the plasma for extraction. And then when we turn the bias off, it reshifts the plasma surface, and those are no longer contributing. So we basically can turn on and off those sources as soon as the plasma has been established. That's just done through essentially what's shown here in the bottom left is just an EPICS page that the operators can use just to turn on and off the sputtering sources. Um, so we do have two sets of these, and so we have some redundancy on the samples that we're using, the metallic samples that we're using, and we're currently developing another set which has a thulium foil. We had some issue with manufacturing and machining a thulium sample to fit one of these coupon shapes. So we're going for a foil sample, which will operate similarly. Um, Now, in terms of these cocktails, and the nice thing about operating an ECR ion source and B, a cyclotron, is we can pack a lot of contaminants. I'll say contaminants because that's what these elements end up being, and they're contaminants to an overall oxygen plasma. Um, but we can introduce them relatively easily and relatively simply and in quantity. A large number of them, as long as they don't have overlapping charge to mass ratios. And so we have to be a little specific about which charge state and which mass state. But we can operate, we can operate our sources and generate a large variety of ions, which cover a large LET range, because you can see the mass varies from oxygen at 16 up to gold close to 200. Um, and then the action of the cyclotron is an incredible mass filter, an incredible charge to mass filter. And so just by making small changes in the magnetic field of the cyclotron at a given RF frequency, you're slightly adjusting the resonance condition to permit one or the other of these elements to actually exit the cyclotron. And so in tandem, we can make those changes relatively quickly. Then that permits us to change from one species to the next within about 10 minutes. And so that's a huge gain in efficiency for our users. And so, but to do that though, we do have to set up our cocktails as we call them. So this is an example here of, let's say, our 19.5 MeV cocktail. That's the one that we've developed originally and that we're currently operating with. Our pilot beam, which is basically forms the base of our charge to mass ratio for extraction, about 0.2. We tune that. So that's our tuning beam. Our pilot beam is our tuning beam. And then as we change the main field by, in this case, plus or minus less than 1%, so this is plus 0.8% and minus 0.95%, it extracts those elements preferentially, and the other ones are still lost inside the cyclotron. We did add neon to our base list in December to add an additional um, um, uh, an additional light element. And we're currently developing now our next cocktail, a 25 MeV per U, slightly higher energy, but it allows some deeper penetration into devices. This one will use an 40 argon 11 plus as our pilot beam, and then allow us to switch between these other elements. And so it'll be um, we'll need to develop perhaps some different gas feeds, but we're definitely going to be developing different ions charge states coming out. We started that development in March. We intend to have that completed this summer and be able to offer it sometime in the fall. Other improvements that we have since made on our ECR source, again on the ion source side of things, is adding a second RF frequency. Now, this one we tested on the Artemis B um, ion source, which drives the, the linac, but it's a similar type of development, and would just need to string some additional waveguides to permit it to use on Artemis A. But the intention here is to add up to about 400 watts, somewhere between 11 to 13 or 8 to 12 or so. It's typically about 10 gigahertz that we need for a second RF frequency. And that does some interesting things with the plasma surface. And basically creates a larger area that we can that's in resonance, from which we can extract ions, and creates some higher fields there so that we can drive heavier elements and to higher charge states for extraction. And so we did some experiments with that on the linac. So here's an example of the installation on the linac. This was a solid state power supply, solid state amplifier, that we purchased commercially. Um, and then this was installed earlier this year. We added additional waveguides to the back of the ion source, which was already primed for its use. So we just had to reconnect some other existing waveguides and string things a little bit differently. But this has been installed now and then tested. So we tested it with light ions and heavy ions, and the light ion being oxygen, the heavy ion being xenon. And we noticed a few things, which was very helpful. First off, that we see a very large increase in the output power on the light ions. And so if you need light ions, adding this additional RF frequency allowed us to generate about a factor of 2 increase in the intensity. So which is nice for light ion drivers. For the heavy ions, though, which are the ones that we're more interested in, we still need to do a bit more optimization, but we noticed about a factor of 2 to 3 increase in the intensity of higher charge states. Now, these are kind of towards the end of the Maxwell-Boltzmann distribution, and so it's the intensity is limited. But this is again, this is developed for nuclear physics applications, and then we apply it towards SEE type of intensities that we need. We're still within the ballpark. So we definitely see an increase in the extracted power at higher charge states. Now, higher charge states are of interest, of course, because we can accelerate them more effectively to higher energies, and that gives us an additional reach with range into devices for these higher LET ions. And so this is um, a development that we're pursuing, and we'll be incorporating into our K500 source in the near future. So if we look at now our operations, so we've been in operations since October of last year, kind of shown here on this graph. We have had one shutdown. So again, it's a new facility, and we're trying to figure out what our maintenance schedule needs to be. So we scheduled some basically reactive maintenance for the spring, and so we had 2 weeks, 2 week down in April, and then we're scheduling a 4 week shutdown in October to November. And as we start to settle into, kind of a steady state, kind of year by year operating profile. But we saw, you can kind of see from here that demand is there. So we started offering somewhere in the neighborhood of about 200, 250, 270 hours per month. And we're filling that relatively quickly. If you look out into the summer, it starts to drop off a bit, but that's just the horizon that the experimental groups have in terms of their boards or devices being ready, or when they're ready to schedule. So I think even since this slide was developed a few weeks ago, we've since filled in, June, July. So we still have time, of course, in the year, and um, we can schedule folks, much farther out. But we're just working with, the existing community, and trying to make sure that we can fit them in when they need it. Currently, we run 4 days per week, so Tuesday, Wednesday, Thursday, Friday, from 8 a.m. until midnight. So 16 hours per day, 4 days per week. And that's a cost savings measure, as we basically try to, create a sustainable program here. Um, our program is fully sustained from user fees. We don't receive any other funding from any other sources. I mean, we're based at Michigan State University, which is a fairly wealthy university, has some deep pockets. It can loan us things as necessary, but we're not getting any operating funds from, let's say, a U.S. government agency, whether, Department of Energy or Department of Defense. The facility was funded through one of these agencies, but not our operations, and so we have to, we're coming up relatively conservatively. So right now it's 4 days per week and 16 hours per day. It's likely we'll initially extend our operating hours overnight, and so now we'll start running 24 hours a day sometime in the near future. We've actually already done a few experiments with that, with operations-based experiments with allowing users to go overnight, and that's worked out pretty well. Um, we do, I think, as folks based in the U.S. know, we maintain a laboratory level of coordination with the other cyclotron-based laboratories in the U.S., which is Texas A&M and Lawrence Berkeley, so that we have at least one facility operable and in operations at any time, and so our shutdowns don't coincide with their shutdowns. We're on track to providing over 2,700 hours in our first year of operation through the fiscal year of 26, which is October to October. And again, as I mentioned, we scheduled through the entire year. The other thing I should just also want to just mention is that it's a dedicated facility. So we're not sharing it with a nuclear physics program or a high energy physics program. This one is set up specifically just for SEE users, and other folks that might be able to use the beamline with these ions and energies. Getting into additional improvements. So this is kind of showing a photograph of our user control room, which is sited right next to the user vault, and so it's really convenient for the users to be able to get back and forth. You'll notice this touch screen panel in both pictures, and that's the main interface that the users have to the experiment, and it's kind of shown here on this larger image on the left, where users are able to manipulate the stage using 4 degrees of freedom with up, down, left, right, in, out, and rotation. Um, we have targeting laser controls, both to calibrate the air gap as well as to identify the beamline center. Positions with the stage motors can be saved into presets and then recalled. And so, a typical user, which might be loading 8 or 10 or 4 devices to test in one session, can load them up out here in the user vault. Use that touch screen to enable the presets and then define the presets. And then once they're back in the control room and ready for the run and the data acquisition, they can just use the touch screen to move to those. Other controls are kind of shown here at the bottom, where there's an end run condition. So users basically they say whether they're going to be running for a certain amount of time, or up to a certain maximum dose, or most commonly up to a certain maximum fluence. Um, 10 to the 7 ions per square centimeter tends to be our the most favorite end run condition, and so that's just how the control system knows when to stop the beam once the exposure is started. And we have online diagnostics, which are calibrated against other intercepting diagnostics, so that we can monitor the flux on a second by second basis throughout the exposure. And so, anyways, the user operates through this panel, and basically just has to contact the control room for access into the user vault when necessary. Here's the live readback that again the users would be seeing on a large screen above that touchscreen panel. There's the live flux and fluence is shown here in this middle graph. There is basically just a reference diagram given the ion species and its energy, and whether any degrading systems are in, and what the air gap might be. And if the users have opted to incorporate a stack up, a list of materials and thicknesses in their device, then this dosimetry system can calculate what the LET versus range curve might look like as well. The species information is kind of shown here, as well as the degrader information. Now, I didn't mention it, but the users have access to basically pneumatically controlled degraders. These are foils which are inserted in the vacuum part of the beam line upstream of the exit window. And that covers a very wide range of basically of attenuation of energy. And it's incorporated within our control system into the dosimetry. It's shown here. So this is on the right is a picture from that user touchscreen panel, where a second window would come up, which then gives a list of the available degrading foils that are used. The ones that are in this dark blue is the range of energy degraders, which still permit the device, or still permit the beam to have some, finite energy at the surface of the device. And if they're grayed out like this, that means the beam has lost all energy before it hits the device. So all a user needs to do is to hit, basically the supply button, and it inserts one or more foils from three different drives into the beam line, and acts then as an energy attenuator. The energies and the LET at the surface and the range computed at the surface in silicon is kind of shown here. That gives the users then some information on what they might be using. The dosimetry we use, so again, the triple degrader ladders are at basically the most upstream part of this three-cross system. We have a four-jaw collimator, which does the final beam shaping before delivery. But those collimation blades are isolated and instrumented, and so we use that um, um, in a calibrated sense, as a means of doing the live monitoring of the flux, which was shown on the last screen. We calibrate them. We calibrate those four jaws against a scintillator and PMT for rate, as well as an idea then of a view screen here for the beam size that allows us to calibrate the flux. Um, Silicon pin stack is also used then to verify the beam energy and the beam species, and to verify that there are no contaminants being delivered to the user, and through the window and the DUT here. Okay, so in terms of what that looks like, so again, it's the scintillator. It's just a plastic. I think it's a PC 404 or 408. Basic plastic scintillator, Hamamatsu PMT. That's basically our counting device, and it's sensitive over a relatively wide range of fluxes that we can produce. The stack of our silicon pin detectors is shown here. And then we use a Con multi-channel analyzer for energy rate and ion species purity measurements. It's a nice system. It has, I believe, 8 channels. And then that is incorporated into our EPIX control system. So it's an online measurement available to our SEE operators or the cyclotron operators. For the users, we now have added an application. So this is a web-based application. Um, we're not actually announcing this until the NESREC conference in July, and we're producing it. We have a paper for it, and at that point, I think it'll be online and live for users. But this is just a preview. Um, so users can use this. Eventually they'll be able to use it from anywhere. It's just a web-based application. We'll have our list of ion species that are available. We have some facility presets for species and energies and degraders at both the KC as well as the FC facilities. And so the ions then are indicated. Degraders can be applied, either aluminum or a tantalum degrader on the FC side of things. And then the users can create a stack. If they're looking at our full beam line, and so this is kind of shown here, we do operate a copper foil, a 10 micron copper foil, which acts as an emittance spoiler and allows us to homogenize the transverse profile of the beam. So, but it does, of course, then interact with the beam as an energy degradation element. Our vacuum window is polyethylene naphthalate, PEN material, about 100 microns of that. And then there may be some air drift. So a stack up can be produced. The target itself could be silicon, it could be GaN, it could be a list of a large number of elements commonly found in semiconductor devices. And so the users can tailor this application to their specific devices if they so desire. The output of this is kind of showing here a list of the energy at the surface of these elements. So, we start with 19.5 MeV per U. By the time you get to the target, based on silicon, it's down to 8.3 MeV per U with a surface LET of about 62 and projected range of 78. That's shown kind of below the screen here on a figure we produce. Again, it's an LET versus range, and depending on where the device sits and what the attenuator, the degrader elements are, this little triangle will move up and down the Bragg peak and the Bragg curve. And so that's design elements that we're providing for the user, so they don't have to run SRIM or anything else themselves. And again, I should mention this is all SRIM 2013 based. We operate up to, again, with both of these two facilities, operate up to energies of about 40 MeV per nucleon. We have, in the course of our development of the linac, and typically for the nuclear physics application, but as far as the linac's concerned, we operate a third of it, for now for SEE operations. And so whatever we do with the linac for nuclear physics has some application for us. So one of the things that we've had to do and had to develop, and this is very useful for SEE applications, is developing a machine learning based algorithm for quickly rephasing the full complement of linear accelerator cavities. And so this is how we change the energy of the beam. The full FRIB linac has about 308 SRF cavities, superconducting radio frequency cavities. And using these tools, we can basically rephase them in about 180 seconds, about 3 minutes. That used to take us about 3 days when we first did this, but with manual scans. But we've got it down now to to a good model and a set of measurements that we make for calibration and confirmation and validation, and we can change that relatively quickly. So that's important on the linac based facility where if we're changing, we basically need to change the energy, change the tune, depending on the charged mass of all of those ions, which operates in a different type of production than our cyclotron-based system does. We have other models that are also affect our trajectory, and so again, it takes information, transverse information from our beam position monitors to allow us to steer and keep the beam centered. And so this is one area that we've been working on for the last few years. There's another set of tools, and this is very busy slide, but we have a very active artificial intelligence and machine learning set of activities contained within the Accelerator physics group, which looks at tuning of multi-charge state beams, which looks at um, um, uh, optimization of tunes through the linac. But what I wanted to mention here from this slide is one application that we've generated is optimizing the output from these ECR ion sources, so these plasma-based ion sources, and basically, using projections, 2D projections with wire scanning data or other types of diagnostics. We can use that to help us reconstruct the 4D distribution of the ion beams as they exit the ECR ion source, which then allows us to maintain or improve the beam quality um, um, for our eventual users. So this is now something that we can incorporate both on the linac side as well as the cyclotron side for all of these types of ion sources. And it's allowing us to basically improve the emittance and increase the brightness of these sources by several factors. Additional developments on the kind of the user sample holding and processing side as we're exploring some computer vision work, both to do a couple of things. One is to generate a beam profile view. So this allows us to take a look in real time, again, using some computer vision models to estimate and to demonstrate to the users what the beam profile will be. So when we're about to irradiate their samples, it's good that they know what the size of the beam is, and so they can compare for overlap. Or if they want to change the spot size a bit by changing the size of those slits that we use. It provides a projected view onto their device so they can make sure that everything is lined up accordingly. And we've also developed a kind of searching and labeling profile, which looks at, specific devices and can assess them and index them accordingly. And that allows us to start to think about automatic targeting, targetry, and exposure systems, where we can analyze a board like this. User could indicate I want to expose this device, this device, this device, and we adjust the positioning stage accordingly, and provide some automated scanning and exposure routines. All right, now moving on to developing of beamlines and facilities. One thing that we've done is just recently we've completed a 5,500 square foot expansion. So if you look at the top level little sketch here, essentially where the beam switch yard is the current user beamline area, user experimental area. So with the new building, we'll be able to increase the number of beam lines to 3, most likely 2 for SEE and 1 for a general purpose beamline. And so this will be expansion opportunities that we'll pursue in the future. We have responded to higher energy ions, and this is, of course, now of interest around the world. At CERN, you have the HEART program with the CHARM and the CHARM beamline. In North America, currently we only have the NASA Space Radiation Line laboratory at Brookhaven. And so we're limited in the number of facilities which can produce very high energy ion beams. And so by very high energy, I mean over 100 MeV per nucleon on up. And so this is an expansion beamline on our third linac segment, kind of shown here in red, which will generate beams up to 300 MeV per U. The light ions, the heavier ions, up to about 160 in the linac. And then produce another, basically shaping and collimating beamline, dosimetry, et cetera, and a user space for experimentation. We're going through the appropriation process now. We expect funding to turn on at the end of summer, and the project to start in the fall. And then given that this is also part of the LINAC, which is supplying the nuclear physics program, we have to basically coordinate with those activities. And so we are expecting completion sometime in 2029. Looking forward from there, we have a proposal out for a dedicated high energy facility. So this is essentially a cut and paste of the FRIB facility, but for much lower intensities than 400 kilowatts. But it allows us to, again, get beam energies up to about 400 MeV per U with these heavy ions. Last slide, I just want to show this. We have programs going on here at Michigan State University in tandem with FRIB and the Electrical Engineering Department in developing a workforce. And so we have a boot camp for training of undergraduate and master's level students. They conduct hands-on experiments using our beam lines. We've done 2 of these so far, and our next session is in September. So I know I'm just really racing through the time. Apologize for that. But I just want to thank you all for your attention, and I'll stick around for any questions.
Great. Thanks a lot, Steve, for the excellent presentation. Very complete and very interesting. So as announced, we will stop the recording here and we will move on to the questions, if that's okay.